and welcome to another one of my Leetcode videos. In this one we will do Leetcode number 315, count of smaller numbers after self. So how the problem goes is you're given an array, an input array, and you need to return an output where corresponding to each element you count the number of numbers that are smaller than this number to the right in the input array. So for example, the first one is 5. So there's two numbers that are smaller than 5 to the right of 5. So there's 2 and 1. So that's why the output here says 2. The next element 2, if you look to the right of 2, only one number is smaller than 2, so that's why there's 1. Next element 6, if you look to the right of 6, only one number is smaller than 6, so we have 1. And finally, if we look to the right of 1, there's nothing, so naturally this will be 0. So yeah, given this input, we have to produce this output. So how do we solve this problem? So the brute force approach is going to be an n-squared algorithm where you pick an element and you scan through the rest of the array to count how many elements there are. But obviously that's going to be very slow because it's O(n) squared. For each one you have to scan through the rest of the array, right? So that's inefficient. Then the next thing that comes to mind is, okay, can we do some kind of sorting, right? But if you think about it, sorting here won't actually help, because if you sort this array and then like try to find, okay, where does like 5 place in that array, it might not be accurate, because like if you look at 6, for example, the smaller numbers could be at the left of 6 and we don't want to count them. We only want to count what is to the right of 6, right? So we could actually extend that idea and do it backwards if you think about it. So basically we keep track of a sorted array, but we traverse this list going backwards and we keep track of a sorted array, right? So we start from the first element and then we add this to our sorted array 1. When we move to 6, we find the position of 6 in that sorted array, right? So the position will indicate how many numbers in that sorted array are smaller than 6, right? And then we keep moving that way. That way, every time we insert an element, we maintain this sorted list, and then the position that we inserted it in will be our index. So for example, our input list is 5, 2, 6, 1. We'll maintain a sorted list, right? So we'll start from index 1. So when traversing index 1, our sorted list will become 1, and the index where we inserted 1 is 0, right? Because we inserted 1 at the 0th index of our sorted list. For the next iteration, we will have 6, right? So inserting 6 into our sorted list, we'll have 1, 6, and the index of this 6 will be 1, because that's where we inserted it. And the index will tell us how many elements are before 6, which meaning are smaller than 6, right? And so the next number is, let's say, 2, right? So inserting 2 in our sorted list will be 1 to 6, and the index will be equal to 1, because we inserted 2 at the index 1, which means there's one element smaller than 6. And then finally, we have number 5, which will be inserted into our sorted list. So it will be 1, 2, 5, 6. And since 5 is inserted at the second index, we'll create index equals 2. So this tells us, if you then look at this answer, that's actually our answer, right? Because it tells us like, okay, for each element, what is the index when you insert it in the sorted array starting from the right. So we just keep adding these indexes that we inserted in to an array in backward, like every time we add it to the front, right? Because we're going backward, and then that will be our final answer. So the time complexity of this, if you look at it, it will be O of n log n, because we will traverse through the input list, right, going one by one, and for each element we'll insert it into a sorted list. So inserting into a sorted list is log n, because we can use binary search to find the index where we should insert it, right? So it will be a O n log n instead of the brute force, which is O n squared. So let's try to code this solution. I will first start by creating the list of integer, which will be our sorted list, right? So this is that sorted list that we talked about earlier that we will maintain, and this will be an array list, and then we'll create a list of smaller to the right, which will be actually be our like resulting list, and this one will actually create it as a linked list, because every time we want to insert at the start of the list, as you saw earlier, we want to read it in reverse. So we will call this smaller to the right and as a linked list, because insertion in a linked list is O1, and insertion in array list at the 0th index can be ON, because it has to shift everything to the right. So now we'll just go through our array in reverse order as we discussed. So now we're going through it in reverse order, and for each element in this array, what we want to do is insert it in the sorted list, right? So we'll make a function called insert and get index, which will insert num set I in the sorted list that we maintain and return the index. And then what we'll do is we'll just add that index to our array, right? But we'll add it at the 0th index because we want to read it backward, right? So as you saw earlier, the index will indicate how many elements are smaller than it, which is what we actually want. And then finally we'll just return this sorry, not index, we'll return smaller to the right. So with this, now we just need to implement this method, which is insert and get index. This is a kind of a standard binary search, so I will just pause the video and paste. Yep, so this is a binary search. I'll just quickly walk through it. So we have our sorted list and our number. This is just an optimization that says, this is actually the case where if the list is empty, then we want to just insert it at the 0th position and return 0. Or if our number is less than the first element in the list, then it is kind of the smallest element, so we just insert it at the start. Similarly, if our number is greater than the last element, then we just insert it at the end. And then this is just a standard binary search. High minus low is greater than 1. We find the middle. We keep moving our high and low. And in the end, the high and low can like get stuck next to each other. So this just determines like what exactly is the index that is less than or equal to our number that we want to insert, accounting for edge cases. So yeah, this is just pretty standard binary search insertion sort. So let's now run the algorithm to see if it works. Compile error. Oh, the method name has to be cool, and let's submit it. Solution is accepted. So yeah, thank you so much for watching. I'll see you in the next one.